Hello, mathematical mavens, and welcome to another episode of Adventures in Algebra. Today, we're going to be taking a look at doing composition and inverses. So the whole point of doing this is so that in our next section we can come up with how to undo an exponential. So we're like taking a little musical interlude into the land of composition to be able to do this. So we're going to start off with composition and then we're going to move into inverses. And really composition is just a new way to combine functions. So suppose you have two functions f of x and g of x are functions. Then, and this is a little bit weird, we define f compose, it looks like a little circle, g of x to be first you use g to x and then you use f. Or as I like to joke, what do you do to x? First you g it and then you f it. I know this sounds a little crazy. You can also go the other way. You can do g composed with f to x, and that means first I will apply f to x, and then I will apply g to x. And that's how we want to read this. We would read this as g composed with f. So a silly way I used to remember when I was a student, working on this is like I always had problems with the word composed. I always accidentally read it as composted. So first you compost F and you put the compost in G. I know that sounds a little silly, but that's the way you should do this. And what this is telling you is, hey, first F, then G to X. Oops, I missed the word 2 there. Sorry about that. My eraser isn't picking up today. That's a little weird. I did the thing where I zoom out. I hope that doesn't make any of you sick. This might seem like insane nonsense. Once we get into doing some examples, this will go better, I promise. So let's do some compositions. So we're going to take a pair of f and g and we're going to find f compose g and g compose f. If you're having a real fun day with this, you could read this as it's fog with a little o, so fog. Like the o is real quiet. And this is goff, but goff, whisper it for fun. I don't even know if that came up on the mic. We're going to find out when I re-listen to this and look for silly or weird things I said. So we're going to have f be x minus 1 for this first pair, and g is going to be x squared minus 2. So I want you to think about the actions that f and g do. What's f do to x? It takes it and subtracts 1. What's g do to x? It squares it, then it subtracts 2. So when we look at the compositions, they're going to do that, but in the order that they appear. So if I'm going to do f compose g of x, that's going to mean that I'm going to first do g to x and then do f to x. Now here's what I'm going to do. I'm going to put g in first. So I know what g is. It's square x and then minus 2. So what's g equal to? Well, it's I square x and then I minus 2. And then I'm going to apply f to this. So what's f do with what you give it? Well, it takes it and it subtracts 1. So I'm just going to take what's inside f and do what it does, subtract 1. And then we'll simplify this. So I've got x squared minus 2 and then minus 1, which is the same as x squared minus 3. Now, if you didn't like that, here's another way to think about this. So f of g of x. So another way you could think about this is like, oh, well, what's f do to g? Well, f takes whatever you give it and it subtracts 1. So it's going to take g of x and subtract 1. Okay, but you know what g is equal to? It's x squared minus 1. So g is x squared minus 1. Or sorry, minus 2. Oof. And then I've got the minus 1 on the outside, so I just replace g with what it's equal to. And then you end up with the same thing, x squared minus 3. Let's go the other way. So now I'm going to do g composed with f. So first f is going to go and then g is going to go. So what's f do? Well, f is x minus 1. And what's g do? It takes whatever you give it and it squares it and then subtracts 2. So I'm going to square the x minus 1 and then subtract 2. So notice how this looks different than what we got when we did f compose g. So if I wanted to at this stage and I wanted to simplify stuff, I really need to FOIL this out. So I'm going to do x minus 1 and FOIL it. So I'll get my my firsts, which will be x times x, so x squared, my inners, which will be minus 1 times x, my outers, which will be x times minus 1, which is also a minus x, and then my last, which will be minus 1 times minus 1, which will give me a plus 1. And then I have that minus 2 from the outside there. And then if I combine all those, I'll get x squared minus 2x plus 1. So I'm hoping that you notice and observe from these two alone, or this example alone, is that it doesn't look like f compose g has to equal g compose f. Looks like they can be different. Let's do another set of these. So we'll have f of x is x minus 1 over 2, and my g of x is going to be 2x plus 1. So first up, I'm going to do f composed with g. So I'm going to take g, which is 2x plus 1, and I'm going to f it. 2x plus 1, because that's what g is. Because I've got g on the inside, because remember this means I'm going to f g. G goes first, that's what g does, and then I'm going to use f. So what's f do? Takes whichever you give it, and then subtracts 1 and divides by 2. So this is what I've got currently. 2x plus 1, it's going to subtract 1 and divide everything by 2. Cool, let's simplify this. So 1 minus 1 will give me 0. So I'll end up with just a 2x left over in the numerator, and I have that 2 in the denominator. And 2 divided by 2, that's just going to be x. Well, that's kind of fun. That one simplifies nicely, doesn't it? Let's try going the other way. Let's do g composed with not g. Although you can gog stuff and foff stuff if you want to. I mean, now it just sounds like I'm talking nonsense. First we're going to f, and then we're going to g. So I'm going to take g, and I'm going to put f into it. So what was f? It was x minus 1 over 2. Cool. And what's g do to stuff? It takes whatever you give it, doubles it, and then plus 2. So I'm going to double whatever is in there, and then plus 1. Perfect. So one thing to notice with the doubling is that I'm multiplying by 2 and dividing by 2. Those two divide out to make a 1. So I'm just going to be left in those parentheses with the x minus 1. And I actually don't need those parentheses anymore because I can do the minus 1 and the plus 1 and just get x. Now, this is unusual, little bit of magic here. Notice they came out the same. Ooh. So sometimes when I do composition, some compositions for some functions, it appears that when I do f compose g, I can get something that works with g compose f. So this is worth noticing that it works sometimes that they end up being the same, which is kind of interesting. You should ask yourself, when is that going to happen? As it turns out, that's special. No secrets in math land today. Yep, it's something. So sometimes, this is just what we've observed so far, when I do my compositions, they come out the same. I'm about to write the same one a second time, but not always. That's kind of fun. So you might want to ask yourself, is there something unique about this f and g pair that made them come out the same, whereas it might not have with others? Let's think about that. Maybe, maybe not. I don't know. Worth thinking about. Let's try another pair, and we'll see what happens. So my next pair is f of x is x squared minus 1, and g of x is going to be the square root of x plus 1. I'm hoping you notice some things about how I've been combining operations here and how things have been moving and what's happening. Okay, so first up, let's do some fog. I'm sorry, f compose g because I'm an appropriate professional. So I'm going to have g go first and then f. So I'm going to do f of g of x. I know what g of x is equal to. It's that square root guy. Cool. And, oh, no, wait, I was about to write something. I was about to do what f is, but, you know, we know what f is. F says whatever you give me, I'm going to square it and then subtract 1. So square root of x plus 1 squared minus 1. Oh, I did this all in black. I've been color coding and I didn't this time. Oops. My bads. Making all kinds of mistakes. When you square a square root, you end up with them undoing each other and you'll just get an x plus 1. And then you'll subtract 1, and once again I got x. Gee, I wonder if this is something like what we saw in B. Let's find out. G compose f, x. So that means I'm going to first do f and then do g. So I'm going to apply g to x, and f and x is x squared minus 1. So remember, I'm just replacing f of x with what he's equal to. These are equal, so they can be exchanged for each other. And then g says, well, whatever you give me, I'm going to add 1 and then take the square root. So I'm going to take what's inside the function parentheses, and I'm going to do just that. X squared minus 1, and then a plus 1. So I'm hoping you notice some things happening here. So I've got minus 1 and plus 1, that'll add to make nothing. So I end up with the square root of x squared. Okay, and hopefully you remember, when it comes to even roots, if I root a square, I actually get the absolute value of x. If you forgot about that, hopefully this is a nice reminder of that. Aha, so once again, we were pretty close this time. These came out not equal though, yeah? But pretty close, right? One has an absolute value and one doesn't. This is actually kind of a special example, and hopefully it'll help you see how things kind of work when it comes to comparing square and roots if you forgot about that. All right, so what I'm leading up to here is a definition of what happens when these do come out the same, and in particular when they come out to both be x. So a new definition. So let f of x and g of x be functions if, when I compose them, so if I do f compose x, with g of x, I get x. And if I go the other way, g composed with f, and I get x again, then we will call them inverses of each other. So then we would say f and g are inverses of each other. So they undo each other essentially and just give back x. And we'll usually write it like this. Usually we will say g is the inverse of f, because we like f for function. And we have some notation for that. We write that as f with a little -1 of x. Yeah, as our g. So we just use the little -1 to mean inverse with where it's at. So notice where it's at. It's in kind of a weird spot. So like this little just means inverse. Of f of x. So notice the -1's like between the f and the x and not like over here like it was an exponent. Yeah. So the way you should think about f inverse is that it's the opposite of f. It's going to do the opposite things. So looking back at like our example B, you'll notice that that was a case where I did have two that were inverses and they were opposite operations of each other. So like, remember what B was? It was, hey, f of x was x minus 1 over 2, and g of x, which actually is f inverse of x, was 2x plus 1. So looking at this, what's happening? I've got a subtraction, then a division. And here I've got multiplication and then an addition. So it's the opposite operations in the opposite order. It's a true opposite of each other. And that's what's really happening here. I accidentally picked something up again. I hate it when I do that. Anyway, some other things to note is that f inverse and f have opposite domains and ranges. So what's really happening is since they undo each other and do the opposite of each other, one of them's x's is essentially the other one's y's. They flip-flop each other, which is kind of cool, you know? So if your f function is like, hey, I'm going to take you and assign you to a partner, then the inverse function would say, okay, I'm going to take your partner and assign them back to you. So if you were looking at some functions and what they do opposites of each other. So just to give you a little picture reminder of how that looks. So if I had my domain here, remember our beans when we were doing domain and range? Oh man, that was a long time ago. We would go from domain to range with f. Well, then f inverse is going to do the opposite. It's going to take the domain to the range. Yeah, that's what's happening here. Okay, so let's do a couple examples where we see how to tell I've got two inverses of each other. And it's going to be very simple, similar to the example we just did. So we're going to see if G is the inverse of F. So we're going to have like a candidate. We want to see if he works. Okay, so for our first pair, we're going to have our G. I don't know why I wrote G first for this one. Okay, 2x minus 1, and our candidate F, not G. I just said F and wrote G. Good job. Oh well, we all make mistakes. It's important to learn from them, like the difference between your letters. Ooh, 2x plus 1. Okay, so this looks pretty good though. It looks like they've got some opposite stuff going. Like I've got my x has got some division, this x has got some multiplication, I got some pluses, I got some minuses. Let's see what happens. Let's do some f compose g and g compose f. I'm always tempted just to immediately write f of x, but you're like, nope, I'm gonna put g in there. It's good. Let's put g in there, speaking of. It's 2x minus 1. That was our g. Okay, so let's take a look at what f does. It takes my stuff. In this case, I've just made it into the X-Men symbol for fun. And do. So whatever I've got, and it divides it by 2, and then adds 1. So I'm going to take what I got, divide it by 2, and then add 1. Now this is a little complicated. I'm going to have to be careful. So let's see. Yep, so I've got 2x divided by 2 and 2x and the minus 1 divided by 2. So I can't really do anything with this. Let's find a common denominator. So I'm going to take 1 and think of it as over 1. And that's got a 2 on the denominator. So I'm going to multiply this by their least common denominator, which will be 2. So multiply by 2 over 2. So over here I'm going to have 2x minus 1 over 2 plus 2 over 2. Let's add those together. So I'll have 2x minus 1 plus a 2 all over 2. So I've combined their numerators. And then negative 1 plus 2 is going to give me a 2x plus 1 over 2. This doesn't get any better. That's as simple as it gets. So immediately I can stop. So stop. I simplified and I did not get just x. So remember from the definition, when I do f compose g, I just better get x. Sorry, I wrote that wrong. It's f of g of x. I better get x, and I didn't, so this is not an inverse. So g is not an inverse of f. So it looks like I'm done with that one. I don't have to do the other composition because I've already had it screw up. So that one did not work. Oh no, I failed to find the inverse. You should ask yourself, I wonder if there's a way to find the inverse. There totally is. It's what we're going to do next. Let's do another pair. It's important to be able to check yourself though. So this is like the check to see if it works step. Like I got to compose them with each other and see if what I got works. So for this one, I'm going to do, I have a minus? Oh, sorry. 3 plus x is plus 2. Sorry, 3 times x plus 2 is my g. And my f is going to be 2x minus 2 divided by 3. Let's compose them and see what happens. Maybe it'll work, maybe it won't. Only one way to find out. And that's to compose f with g. So remember, this means we're going to apply g and then f. So g gets to go. What's g do? G says I'm going to take your x and I'm going to multiply by 3 and then add 2. And what's f do? It says, hey, whatever you give me, I'm going to subtract 2 and then divide by 3. So I'm going to have a 3x plus 2 minus 2 and then divide by 3. This is looking a little more promising because 2 minus 2 is nothing, so that'll give me just a 3x over 3. Oh, and 3 divided by 3, that divides out to a 1. I don't write 1s, you can't make me. There's an x. Actually, if it's adding 1, I should write it. I'm joking. Okay. That looks good. So one of them worked. Let's see if the other one works. So I got to do g compose f. So let's put f into g. What's f do to x? It subtracts 2 and then divides by 3. So I have to take that and put it into g. And g says whatever you give me, I'm going to multiply by 3 and then add 2. So you really got to track these operations, the additions, subtractions, multiplications, divisions, very carefully. When in doubt, replace the x with what it's equal to, or the g or the f. So I'm dividing by 3 and multiplying by 3. Those two will divide out to a 1. So I'll be just left with an x minus 2 plus 2. Usually one of these is easier to do than the other. I think this is the easier one. I got a minus 2 and a plus 2. That's going to add to nothing. This is an x. So this second check. Okay. So it appears g is the inverse of f. So we would write f inverse is indeed 3x plus 2. It's just a nice way to write it to confirm, yes, I know that this is the inverse, so I'm going to write it with proper notation. So we found one. We found our first set of inverses by just sticking functions in each other. Boy, does that seem like a non-efficient way to do this. We're going to do how to solve for ones next, so, it'll be good. So my last one I probably should have did first. This is the simplest one. I actually have a note on my notes to do this one first. Awesome. F of x is 6x. G of x is x over 2. Oh, or x over 6. Sorry. The amount of self-judgment I have right now is horrible. F compose g of x. Okay, so this is f of g of x. And g takes x and divides it by 2, so we're going to have that happen first. I have said divide by 2 again. It's dividing by 6. And what's f do? It's going to take whatever you give me and multiply by 6. Usually when I teach this in a room where I actually see people, I do like dance moves and I remind you that, hey, if f is like take 2 steps backwards, then g has got to be take 2 steps forwards for it to be the inverse, because you got to get back to where you started. Speaking of which, that means you just get an x back. So that's another way for you to think about this is, oh, these are both doing stuff to x, and if they're inverses, if they do opposite things to each other, you just end up with x back because they've undone each other. They've done the opposite. They've taken you back to what you started with x. Let's go the other way. G, and we're going to do f first this time. What's f do to x? It multiplies it by 6. Okay, now we got to g it. What's g do? It takes whatever you give me, divides it by 6. Stuff, good times. 6 divided by 6 is totally a 1, so we end up with just an x. We appear to be in happiness land. G is the inverse of f. So we'd write f inverse of x is actually the function x over 6. Good times. And it makes sense. If f is let's multiply, then g better be let's divide, if they are true opposites of each other. I keep accidentally picking stuff up. What I want to do is scroll. Scroll. So you might ask yourself, if I just have one function, how can I find the inverse? So one thing that's going to help you out with this is that essentially, remember, inverses need to do the opposite in the opposite order. So the steps behind this are actually pretty simple, but essentially what they're going to do is they're going to make x and y, or f of x, switch. So first we're going to write y for f of x. And then here's the fun part. Switch x and y. Because if the inverse is going to do the opposite, then it's got to switch these two. Next, you're going to solve for y. And then last but not least, you're going to write f inverse of x for y. And that's the steps. So I'm going to do an example right next to this so you can see the steps as they happen with something where we've already seen the inverses work. So I'm going to actually start with our example C. So in our example C, we had that f of x was 6x. So for step 1, I'm going to replace f of x with y. So y is 6x. For step 2, I switch x and y. So wherever there's a y, I'm going to put an x. Wherever there's an x, I'm going to put a y. And now I'm on step 3, which is solve for y. So I'm going to just take this and divide by 6 on both sides. So I get that y is equal to x over 6. And I wrote this kind of backwards on purpose so you could see the next step 4 a little easier. Step 4, hey, we're going to write f inverse in place of y. So I'm just going to replace this y with f inverse of x, which is x over 6, which we already saw in C was the correct inverse. So happy times, we know this is correct. So those are the steps. I'm going to do this with some more complicated functions so you can see how this works. Once again, didn't mean to touch that. Just want to scroll. Let's do some examples. So we're going to find the inverse of the function. So first up, we're going to have f of x equals 2x minus 7. So hopefully you're picturing like some idea of what this should look like, but if not, that's okay. We're going to go through and do the steps. First step, let's write it with y instead of f. This is just so you don't have that clunky f of x notation floating around and you might accidentally think an f of x is a times x, if you know what I mean. Step 2, switch x and y. So this is going to be x equals 2y minus 7. Step 3, let's do some solving. So if you remember, for solving linear equations, I need to solve for y, which means I should add the 7 first. You always want to do your additions and subtractions first, and your multiplications and divisions second. 2y. Okay, so I've got 2 times y. To get rid of a multiplication, we're going to do a division. So we're going to divide by 2, and we're going to divide by 2. Now that I've got y by myself, I just need to write this in inverse notation. So f inverse of x is going to be x plus 7 over 2. So there's our inverse. Not so bad, I hope. And it looks like it's right. So what we were talking about earlier is how it needs to be opposite operations in the opposite order. So if you look at what's happening with the original f, it's like, oh, I'm going to multiply by 2 and then subtract 7. This one's like, hey, I'm going to add 7 and then divide by 2. Opposite operations in the opposite order. Let's do another one. So for fun, I call this one g. Don't worry, g can have an inverse too. 4x. I believe in you. We did one similar to this earlier. So first up, I'm going to write g of x instead with a y. I'm going to do my switcheroo. And now I need to solve. So I'm going to divide by 4, divide by 4. Lo and behold, y is equal to x over 4. So what I should do is write this in inverse notation. Since my original function was called g, I'm going to write g inverse is x over 4. Now if me switching to g messed with you, it's okay. I'm going to go back to f. Don't worry about it. I mean, I should be able to name my functions whatever I want. I should call them all r because, you know, my name. But watch me not. Let's do 4x cubed minus 1. This one should require a couple more steps, so we're going to be careful with this one. Okay, so first up, write y for our function. Then I need to switch x and y, so x where y is, y where x is. Now if you have multiple x's or multiple y's, make sure you switch them in every location, not just whenever. You probably won't though, it's okay though. So let's go ahead and start solving. So I need to get y by itself. It's being cubed, then multiplied by 4, and then subtracting 1. So I got to get rid of the addition first. Whatever happened last, you get rid of first. That's the principles of solving. Cool. So y is being cubed and then multiplied by 4. So I'm going to divide by 4. Oh, I'm going to have to move this up and run out of space. Divide by 4, divide by 4. Why do I say 4 weird? I don't know. Aha, now I have y cubed. How do I undo a cube? Well, you could do this one of two ways. You could put everything to the 1/3 power because 1/3 times 3 will end up being 1, or you could do the cube root. I'm going to do the cube root because I know the cube root of a cube just comes out as y. So I'm going to cube root both sides. Actually, I meant to do that in a different color so you could see the step as it happened. Sorry about that. I like to color code so you can tell what the new action was. So the cube root of a cube, those two end up just giving you back what you started with. So now for my last step here, I need to write my inverse. So my f inverse of x would be the cube root of x plus 1, all divided by 4. Well, that's kind of a new one. Does it look right? Well, yeah, because what's f? I'm going to cube what you give me, multiply by 4, and then subtract 1. This one is, hey, I'm going to take what you give me, I'm going to add 1, divide by 4, and then do the cube root. Opposite order of opposite operations. Okay, just to hammer home that inverses do the opposite of the original, let's do a little bit of a graphical example. This should be fun. I like graphs. So suppose you have the points 4, 2, 6, 3, and, ooh, I need another comma, 8, 4 are all, that's not how you spell R, area, all on the graph of f of x. Give 3 points that'll be on f inverse. This is not a trick question, so take a second to think about it while I roll this up a little bit. And we'll make note of what's going to happen. So remember what the inverse has to do. So if you're thinking about what f is doing, by looking at these points, what this says is, well, f is going to send 4 to 2, and f is going to send 6 to 3, if you remember our dot stuff, and f is going to send 8 to 4. So in thinking about what f inverse has to do, it needs to go the opposite way. So it needs to go here to here, here to here, and from here to here, which tells you f inverse of x will have the point 2 goes to 4, 3 goes to 6, and 4 goes to 8 on its graph. It needs to do the opposite. It needs to send my y's back to their x's if this sends my x's to their y's. If f sends x to y. I hope that gets you thinking a little bit more about what an inverse does. Just to reiterate what we've done today, we've discovered what a composition of functions is. It's sticking one function inside of the other and seeing what they do. Sometimes when it's special, it comes out to x, and if it does it for both orders of the composition, so if you do f of g and g of f and they both come out x, you have an inverse. And if you want to find an inverse, there's a nice 4-step process that'll get that for you. I hope you had a good time and you learned some amazing algebra. Bye!